Hi everyone, welcome to the last talk in this series on singularities. We'll hear from Christoph Kehle, who's an assistant professor at MIT, on the cosmic censorship conjecture in the context of gravitational waves. Really excited. Take it away.
Yeah, thanks, Bertrand, for the introduction, and also it's an honor to give the last part of this field for its lecture series on energy condition and singularities. So I will speak about the cosmic censorship conjectures and present a more modern formulation, and I will do that in the context of gravitational collapse. So I will not speak about cosmology and all these other things. They're also interesting, but for this purpose, for the purpose of this talk, I will speak about cosmological about gravitational collapse, the cosmic censorship conjectures in that context. Yeah. So as opposed to last time, where we only assumed. So in your talk, we only assumed mostly inequalities of the Ricci tensor, where we introduced the Penrose singularity theorem, or as I would like to refer to it as Penrose incompleteness theorem. Now we will actually propose an equality, namely the Einstein equation. We all know and love. So I will write it with the cosmological constant in this case. But mostly for essentially all of the talk, lambda will go to 0. So we look at the asymptotic with that setting. And I would like to present those cosmic censorship conjectures in what I view as the modern formulation and the correct formulation, and in this sense, as formulation using fundamentally the well-posedness of the Einstein equations. And more precisely, what has been shown by and then later also together with Gerard. So this is from 1969. So the first was the existence, and then the second one was maximalization. So this means that if we have, so they prove that if you have initial decay data for the Einstein equations, which consists of a 3-manifold, the Riemannian 3-manifold together with the second fundamental. It's going to be a second fundamental form. And also we need initial conditions for the matter field. At this point, I'm not specifying what matter we're looking at. But yeah, so let's leave it open for a second. So they proved that given such initial data, there exists a maximal, unique MGHD, which is a maximal globally hyperbolic development. Four manifold M4 together with the Lorentz metric G and matter fields satisfying. Yes. So I will. So this is actually quite a remarkable theorem. That, yeah.
Just a quick question: is it important that it's three-dimensional? Do they prove it in general dimensions or just for three?
I think you can prove it for more general, but yeah, so this is. No, but okay, we're interested in the three-dimensional case in the context of gravitational collapse. And in fact, sort of this actually, we want to have topology R3 most of the time. I mean, this is sort of the interesting case of gravitational collapse. The initial data are posted on R3. In fact, if you think of Schwarzschild, then actually you realize that the maximum extent Schwarzschild solution, you cannot think of arising from R3, but rather from data on R cross S2. Okay, so this is sort of, so the nice thing about also this is that actually, by definition, this maximum globally hyperbolic development is in fact globally hyperbolic, and it's also maximum in the sense that cannot be embedded into another globally hyperbolic development, such that the embedding is a problem. Okay, so in that sense, it is also max. And I think this is quite a remarkable theorem, and does not have analogs, let's say, for other equations.
Christoph, are there any conditions on the boundary conditions of the data? Like, are things falling off so that it's asymptotically flat, etc.?
So I will assume throughout the talk that we are looking at asymptotically flat. But actually this is now, I think, I think you can construct something very general. This is like you patch together local solutions, right? And by the domain dependency, you can just patch together. And that's how it's constructed. So, okay. So last time we already saw the Oppenheimer-Snyder collapse. I think we did, right? We talked about it.
I think so, yeah.
Which now I would like to put it into this context. So I don't write the full Penrose diagram, but I'll think about it as thank you. As arising from initial data. And the Penrose diagram looks as follows. Here's our data. That's the support of the dust. So I should say this is a solution, the Oppenheimer-Snyder solution of the Einstein equations coupled to dust. So this is Einstein dust, where the dust has a distribution which is in fact homogeneous in this region and then equal to 0 there. So it's not a smooth solution, but okay, that's fine for the moment. And here we have this R equal to 0 singularity. So this describes actually the formation of a black hole from detectable data post on R3. Okay. So we learned last time about Penrose's incompleteness theorem. So what does it? Let's review it very quickly. The context of the maximum global hyperbolic development, namely if your matter, if your initial data surface sigma 3 is non-compact, so in particular, for instance, if it is R3, like in this case, if moreover we have well, the energy condition on the Ricci tensor, which the null energy condition for the Ricci tensor is exactly null energy condition for that. This is equal to 0 and null vectors. So this, if you have the null energy condition, and if you have the trapped surface, either in the data, already in the data, or also in the maximum global hyperbolic development, either of those, then we know that the maximum global hyperbolic development is incomplete. Okay, so that is what the incompleteness theorem tells us in the context of the initial value formulation. So maybe we should, I would like to see it. So here actually the incompleteness, first of all, this spacetime has trapped surfaces and it satisfies all the conditions here. So it has to be incomplete, and the incompleteness arises due to the singularity. Okay. This theorem doesn't tell us that there is a singularity, it tells us it's complete. And actually, cosmic censorship conjectures will exactly address the issue and the issue of the completeness. Why, like, what's the reason of the completeness? Okay. So a nice corollary actually of the Penrose's theorem is the following, namely that the completeness, incompleteness Oppenheimer-Snyder is stable. It's not quite true because somehow the regularity, I said, the regularity here is actually not so great, but let's forget about this issue for a moment. So this means, why is it stable? It is stable because if I slightly perturb the initial data here, let's forget about the regularity issue. And the point here is that actually a trapped surface is a condition which is a strict condition, namely that the outer expansion is negative. And moreover, it involves closed surfaces, contact objects. So this means that this condition will also be satisfied for small perturbations of the initial data. Even if you have a trapped surface not on the initial data, but also future evolution. This means that if you slightly, by Cauchy stability of the equations, continuous dependence on the solution on the initial data in any contact domain, you can prove very easily that in fact, if you have a trapped surface there, then small perturbations of the initial data also lead to a trapped surface there. So this is why the incompleteness, this theorem actually tells us that the incompleteness of Oppenheimer-Snyder state, and this is sort of the market aspect. Yeah.
Regularity actually appears in a Penrose singularity theorem. Sorry, incompleteness theorem. I mean, it's just a statement about, as far as I know, it's just a statement about the null energy or the null convergence condition.
Yeah, but exactly. I mean, you need to, okay, what's the regularity here of the metric, right? I mean, even to define something like curvature, you need C2.
Right, so as long as it's like, as long as you have a well-defined distributional curvature, I would have thought you can still apply Penrose.
I think actually this is, I don't know if people, okay, so not Penrose as it is written in his paper and as it's proof, that certainly requires, I think, C2. I'm pretty convinced that there are weaker formulation, which I don't know off the top of my head, of Penrose's incompleteness theorem, which allow for weaker formulations of the conditions, and indeed that's why also I think it's not an issue. Yeah. But yeah, I think I'm not actually. I think these questions are not as easy as they appear sometimes. So these low regularity Lorentzian geometry can be quite tricky.
Actually, Christoph, in what sense is the initial condition low regularity for Oppenheimer-Snyder?
In the sense that the rho,
yeah,
rho is constant here, and then it is equal to 0 there. Yeah.
Yeah, but I'm sure you can just add a little bit on top and.
Well, that's not Oppenheimer-Snyder. Then you need something else. So I will talk about a smooth solution, more regular solution to Einstein less than a second. In fact, this has been done by Christoph Kehle. And but let's say maybe I shouldn't have I should just have ignored it, but okay. Okay. So what did I say? Yeah. Yeah. What is also sort of an aspect of Oppenheimer-Snyder is that we have the singularity R equal to 0 there. That's a very strong singularity. And in fact, sort of the right way to capture the strength of the singularity is in terms of inextendability of the space-time. So in fact, you can prove, well, I don't know if that's proven. It's proven for Schwarzschild. So I think I mean, okay, I don't know, actually it's proved in this case. But the claim is that that Oppenheimer-Snyder is C0 inextendable to the future. Okay. So that this singularity is so strong in the sense that does not exist a bigger manifold which you only require to have C0 metric such that this and that's proper. So this actually classifies the strength of the singularity. It's easy to prove that it's C2 inextendable because the curvature blows up. If you know the curvature blows up, the Krafft scalar, for instance, and C2. But you can actually also prove that it's C0 inextendable, like the Schwarzschild metric. I think, well, that's already proved. I think it's actually not proved for the Oppenheimer-Snyder, but I think this can be done. Another thing which is important about the Oppenheimer-Snyder collapse is that the incompleteness of it is hidden behind the event horizon. So it means the incompleteness or the singularity in this case is hidden behind the plus. Okay, behind the plus. So these are actually quite the best you can hope for in the presence of singularity. First, that there's actually a genuine singularity, and think about sort of what it means to be CH0 inextendable. It means that you're torn apart by tidal deformations. The observer reaching singularity are torn apart by tidal deformations. And so C2 in extendability, so if you only blow up in level of curvature, it means that for an instance of time, tidal forces are infinite, but it does not necessarily mean that tidal deformations are infinite. So you have to integrate the Jacobi equation twice to get the geodesic deviation equation twice to get tidal deformation, and this is why this strong similarity at I equal to 0 means that you're truly torn apart by infinite tidal deformation, and now you have to use your favorite quantum gravity to now continue further what happens to the observer. And moreover, also is that sort of faraway observers.
What does it mean to be that the tidal forces are infinite, but they're not, they don't tear you apart?
Well, you have to, I mean, this is sort of just that, I mean, it's just that, okay, if you can have an infinite force for an infinite small amount of time, which gives you a finite, I mean, it's just an integral.
Okay.
You have to integrate twice, in fact, to get from the forces to the displacement. I mean, this is also in Newton's equation, F equals m double x double dot. Okay. So now, sort of, okay. So the cosmic censorship conjectures essentially say that the good properties of Oppenheimer-Snyder hold at least generically. So that's sort of maybe the essence of it. And okay, so let's state those conjectures in the modern formulation.
So one more clarification. Incompleteness is different from singularity, right?
Yeah.
Okay. But what exactly is incompleteness? Are we saying that it cannot be extended, or are we saying we don't know if it can be extended?
Incompleteness has a very precise meaning. It means that there do exist geodesics,
Yeah.
which only live for finite proper time.
And cannot be extended. You can actually prove that
Yeah.
they have to cease.
Yeah.
Okay.
And these are exactly the geodesics which
Right, right.
so all geodesics which don't go into black hole is correct.
Actually, let me ask a follow-up to that. So normally, at least when I was growing up in the GR literature, we defined singularity as completeness.
Yeah.
So
Yeah, if you, I mean, that's sort of by definition, that's geodesic incompleteness. Yeah. I mean, that's what I call geodesic incompleteness. But yeah, I mean, look, singularity doesn't have a very precise mathematical.
right, okay, so I was gonna ask.
Typically, I would like to refer to it as some extendability.
Right, but in extendability of what, of geodesics, and then you're back to the geodesic incompleteness, right?
No, an extendability of the metric.
Metric.
And sometimes the singularity can be traded off by a conical singularity.
Yeah,
So
So let's take the weak. Let's first take the weak cosmic sensitive convection. So this is actually sort of this formulation. So it's originally the Penrose thing. But this modern formulation actually goes back to Garoff and Horowitz. And this is sort of the, and also later to Google. But I guess sort of the idea of it defining it the following way goes back to maybe the PhD thesis of the. So it says that for generic, asymptotically flat the data sets. Now infinity is complete. Maybe I should say it a bit better. I'm sorry about that. The MGHD, I stress so much the MGHD that I should at least also use it. So the MGHD, maximum global development, has a complete non-infinity. So here, this is also what we have here in the Oppenheim Snyder collapse that I plus now infinity is complete. And so this is actually quite nice formulation because you don't even, the only thing you need is sort of this notion of more infinity, which you sort of always have if you have asymptotic flat data. So we don't have to go to singularities or event horizons or all any of those kind of things. Okay. Strong cosmic censorship conjecture. Okay, maybe I should say here that some generic in the weak formulation was actually not introduced, I think, in the original paper, because it was not known whether one needs it, and it actually was introduced by. Well, actually, I don't know exactly, but yeah, it is certain.
Actually, so can I ask something that's also not in the, but in the original paper? So the original paper preferentially refers to scribe plus, even though it does not refer to scribe minus. It kind of makes a big deal out of saying that we don't think it's true for scribe minus because of the Big Bang singularity. If it could exist in asymptotically flat space, I always found that very unsatisfying because we expect that there should be time reflection symmetry, or just the equations of motion don't preferentially pick up past versus future. Is this still the way that it's normally formulated?
Well, it's certainly in the context of gravitational collapse. So where you know.
But this doesn't specify gravitational collapse anywhere, right? It just says that this is true.
I mean, yeah, I mean, this, okay, this also, it says, okay, you look at asymptotically as. So now you want also an I minus there. Okay.
And just imagine like a scribe minus, and then you have a bit of a scribe minus and a past singularity. I mean, I agree we don't have solutions that look like that, but it doesn't seem crazy for them to exist, right?
Sure, you can also by, as you said, by time reflection symmetry.
Right.
But yeah.
It just seems strange with the Big Bang singularity to propose something that would rule it out.
Yeah, but okay, then you have to look at the cosmological setting as well, and maybe and also here you have the asymptotically flat initial paper.
You want to say the asymptotically flat is what rules it out in a sense.
Okay. So, well, I wanted to write here. So here we write for generic asymptotically flat. Remove the data. Is inextendable. That's a zero Lorentzian manifold. So now I use the specific formulation in this in formulating the strong cosmic censorship conjecture motivated by what we've seen in Oppenheimer's matter collapse. So I now postulate that for generic asymptotic flat initial data, MGHD is extendable as a C0 Lorentzian manifold, so a very strong version of formulation. It's called the C0 formulation. Turns out that actually this conjecture is false. And this makes it interesting, and it has to be reformulated. But for the purpose of pedagogical purposes, I believe it as it is now. So this is the very strong formulation, which was motivated by the Oppenheimer Snyder.
Christoph, how does this say anything about the singularities? So can this admit singularities as written?
Yes. For instance, this is an example
Right.
for which the MGHD is inextendable as a C0 Lorentzian manifold. Another example is Schwarzschild.
Yes. So this is not a statement about like no singularities even inside horizons.
No, this is a strong cosmic censorship.
Okay, right.
Maybe I should say that if it's weak and strong, there's maybe a bit unfortunate because neither does weak imply strong nor does strong imply weak. Even though good luck proving strong without weak, but
So how I'm a little bit confused. How is it I thought that the cosmic censorship should be related to the existence of horizons, right?
Mhm.
So where is the horizon, especially in the weak one?
Yeah, I mean, I will give you later counterexamples to, or like not counterexample, actually, examples why generic has to be there. Maybe I should say that by formulating it this way, trivial things like negative mass water or so on, you don't even look at it. Because you see that negative mass water, you cannot obtain from regular initial data. I mean, more, so you cannot find regular initial data for which this arises dynamically. So this I claim is the right formulation of weak and strong conjecture, and it sort of exactly captures the phenomenon of the dynamical formation of naked singularity and postulates that this is a non-generic phenomenon. So earlier, the genericity has always been assumed on the level not of data, but rather on the level of the solution itself. But this actually never really worked out because it's not even, there's no, what solution to include and what not, and there hasn't been the right consensus on how to formulate it correctly, and I claim that exactly using the dynamical formulation of the Einstein equation, these have this natural formulation. So let's stay in the model of the Einstein dust. Unfortunately, I don't want to erase it. It's pretty. So now we look at Einstein dust system, and I would like to present some early works from the 80s of Christoph Kehle on that system. Now Christoph Kehle in this model, he looks at different initial distributions of dust. And in this case, he doesn't assume that in fact, assumes that the dust is a smooth function. The initial distribution is a smooth function. And moreover, in order to prevent shell crossings, which we talked about earlier, he assumes that, in fact, the derivative of rho is actually negative. In this case, you can rule out that, that you have shell crossings. And then he actually proved the quite remarkable thing. He proved, so this is in supersymmetry, Einstein dust. So then he proved that both weak and strong cosmic censorship wrong both in Einstein dust and supersymmetry. Actually, in this restricted class where you don't have shell crossings. And he proved that actually if a certain quantity, namely the second derivative of rho at the origin has to be non-positive. So if it actually is negative, then you get dynamical formation of naked singularities. And more precisely, the picture looks like this. Now I start looking correctly. So this is the Penrose diagram. So you have your initial data there, and then your I plus is incomplete. What actually happens is that all the dust forms a singularity at the center. And this is R equal to 0. It forms a singularity there. And actually, once you have a singularity, the MGHD actually stops. Okay. Because once you have a singularity, you cannot continue a little further because
the equations break down.
So this is why actually in those formulations, you never entertain time singularities. Then the notion of time-like singularities does not exist in the dynamic formulation of the answer, just because you impose MGH. Yes.
So, when you write complete non-infinity psi plus, does it include part of the horizon that develops because they are connected, right?
So what is the notion you're asking? What does it mean to be incomplete with no infinity?
Or maybe in this version, what does it mean complete non-infinity?
Yeah, what does it mean? That's the question.
Yeah.
Uh,
It can contain part like it.
No, it does not contain the horizon. So what it means is there are various ways to define it. And sort of either you embed it conformally in some bigger spacetime, and then you can actually entertain the notions of geodesics or rescale geodesics there, and they're geodesically complete. Or another way sort of is that you shoot out. You look at an outgoing cone and shoot geodesics in this direction. And the claim is that their affine time is infinite.
No,
Affine time.
time.
So this is just I mean, it's just
Yeah.
it's just the natural notion of what you expect I plus to be. And it does not, you sort of the claim is that there's not geodesics which reach like on I plus which reach this point in finite affine time. And
Yeah, but this is why I thought that it's not clear how to separate the black hole horizon from.
so again,
sky
I mean,
plus.
what you do is you can either do it there, you shoot geodesics inwards, normalized suitably as you go to infinity. So that, and what happens is that their affine time grows to infinity. This is the
Yeah,
definition.
yeah.
And exactly what happens here is that the affine time, as you look at such geodesics, has a uniform upper bound, and this means that I plus is infinite. Another thing is, so this is why it violates recosmic censorship, and moreover, exactly because you only have, for generic initial data, at least in the class he considers, they're generic because it's just this inequality here. You have this picture. And moreover, what you have is that actually this cone here is extendable in the, I think even in the smooth case. So you can find a bigger Lorentzian manifold. I think smooth even for which it is embeds properly into the bigger one. And this is why it also violates the strong cosmicity. Okay. But the reason actually why this violates is because it's a bad matter model. And it's not bad matter model. And everything is due to the density becoming infinite at the center. But if you look at more realistic scenarios, you would also impose pressure. So that once the pressure kicks in, the density does not come. So so this is why this solution is actually bad matter model. In addition, that it develops those, okay, what we talked before.
But it does satisfy the energy condition.
It does satisfy it.
And you call it bad.
Well, I think not all.
Does it come from Lagrangian? Can you write on Lagrangian for this?
Well, it's not a field. I mean, you can write. I don't think it's like a field theory.
Yeah.
But that's okay. I mean, they're good. Like the class of equations, a nice line, in my opinion. For instance, also.
There's one reason to call it bad
No,
math.
that's
You
for me
can't run on
personally.
Lagrangian.
That's
Also, it's not representative because there's ODs and no PDs in it. Yeah.
Okay, maybe I should mention here. Okay, well, let me see if that's what I planned. Okay. So, maybe I should mention here that there's a recent result. Also one that I talked about recent results by Guo Hadachian. Who construct, so in there they have an equation of state of this type. Where the pressure, they have non-zero pressure. Epsilon is a small quantity, and they construct naked singularity also for the Einstein other equation with an equation of state of physics. So you think that dust is exactly where epsilon is equal to 0. So there do exist, So this is something, okay, it's much more difficult. But so there do exist naked singularities.
So this is also in spherical symmetry.
Yeah. Okay. So Christoph Kehle then went on to entertain a better matter model. Namely, now a matter model which Meta will be happy about, because it has a Lagrangian. And so this actually Newton's, I guess he even started in his PhD to study. So the Einstein scalar field model. And in this matter model, actually he proved. So this is in spherical symmetry. He proved that weak and strong cosmic slit, weak and generic is nothing. So this is the Einstein scalar field model in spherical symmetry. So it proved that well, there exist solutions which again have these naked singularities. I plus is incomplete. And then he also constructed other solutions. In fact, I mean, he constructed various kinds of solutions to this model. He also constructed solutions of this type. Where you have a piece of Cauchy horizon inside and which across which you can actually also extend. So here dissatisfied. This is a counterexample to weak cosmic censorship if you drop generic, and here you had a counterexample to strong cosmic censorship because you can extend. That's something I tell you of a strong cosmic censorship if you drop generic. Okay, so he constructed these examples, and so more importantly, he showed that due to some blue shift instability along this backward light cone here. So it proved that once you have this type of situations where you have light first singularity there, and then this property that and no trapped surfaces in particular, then this is unstable, and in fact there's a blue shift instability associated with this light. So if you think of the geodesics reversing there, then in one sense, light signals to this guy, then these light signals are infinitely different. So this is what you use in order to prove that those situations are exceptional and can be perturbed away in that sense. And so actually, this is quite a remarkable series of works where he actually proves weak and strong cosmic censorship. So this was in the 90s. I should say that the Einstein scalar field model in spherical symmetry and versions of it have always been seen as a toy model for the Einstein equations, as opposed to like a genuine matter. So we don't think of this as the reason why we study it is not because it's the matter we're interested in, but rather because the dynamical degrees of freedom propagate as wave equations. So this we should think of for example for the Einstein equations. And in fact, I recently showed actually by Rotman or by Rudniansky and Schlappendorf. Rotman showed that actually there exists naked singularities arising in the Einstein vacuum. So this is quite a remarkable. It's a very remarkable result. So I think this for Einstein vacuum. Their mechanism is inspired, of course, it's far more complicated because you don't have access to spherical symmetry for the Einstein vacuum equation, so you really have to study the announcement, the spherical symmetry part. But there is a certain dictionary which we use to translate behavior of this Einstein scalar field system in spherical symmetry to the Einstein vacuum equation. And one can sort of argue that actually their construction is motivated by the construction of crystal. So it also has this feature. What is interesting though is that all of those constructions rely on low regularity of the initial data. In fact, the initial data in all those constructions are not smooth. There are VV sort of sums, low regularity. The regularity is still fine in order to have well positives of the equations and also stability of Minkowski space, but it is of low regularity. And also this mechanism of using the blue shift instability to perturb away those solutions fundamentally requires low regularity perturbations. So it is a very open and interesting problem to understand both the formation of naked singularity as well as their instability for smooth initial data. But this is something we don't know. There's a
Sorry.
there's a numerics by Chaptuik actually, which I want to come back later.
Do they assume do they assume the dominant energy condition?
Yeah, and this satisfies the dominant energy. But I think this is not so relevant.
I mean, it must be false for null because you can have false vacuum decay. So
I'm sorry, what?
you can have false vacuum decay, right? Like a bubble of a negative cosmological constant nucleating inside the asymptotically flat space if you allow for not null but not dominant.
So you want to impose now a cosmological constant? That's it.
Well, it's still asymptotically flat. But
But if you
have just a null energy condition and not the dominant energy condition, then you can have a solution where there's just a bubble of a negative cosmological constant expanding inside, and that violates. I mean, that will result in a singularity that reaches it'll destroy square plus eventually.
Okay, yeah, these solutions you have to tell me later about the medium.
So, Christoph, can you say a little bit more on this, the initial data in this case? Like it's gravitational waves or?
Here?
Yeah.
Yes. I mean, this is reach equal to 0, so you should think of it as gravitational.
So, and they're compact and non-spherically symmetric and that's it.
And what do you mean by compact?
So are they restricted to some, do they fall off
They're asymptotically flat.
asymptotically flat?
In fact, they pose it on a characteristic data, but you can think of it as posing data on this. I mean, from characteristic to pushy data based on. There's quite remarkable.
And is there some specific arrangement?
So this is based on a this is based on a self-similar
Right.
scaling actually
Yeah.
along this mathematical.
Right.
They have an analogous distance of similarity along also along this. So how they prove it is they set up the data there on this conjoint, and then they prove the existence of the exterior region, and then also they have the glue in the interior region. So this problem actually is not like classical. So so there's something, but it is actually quite remarkable. But again, this uses also, so you can prove that those solutions, they're not C infinity across exactly that like, and they're fundamentally used also. Like they're everywhere smooth except across this fast light not smooth. Okay, so let's
Actually, Christoph.
Yeah.
A very basic thing which is kind of bugging me. This whole generic business. Right? There's a conjecture. And I think one of the classic ways of disproving a conjecture is to find a counterexample. Right?
yeah, in this case you have to find an open set, yeah.
That's the thing. You can find the counterexample, as we said, Christoph
No, it's
Kehle
not
did the spherically symmetric problem, and he said, yeah, sure, I can get naked singularities which are visible at infinity. But then what you're saying is, oh, that is a very special solution. So you should give me the freedom to cut out every special solution that I don't like, and then I'll prove that the rest of them satisfy my conjecture. Isn't that really what's going on here? Or
Well, I mean, it's the best you can hope for in the
Okay.
present. Okay. It would be nicer for logical purposes if you prove the conjecture without the word generic, but you can't. I
You
mean,
can't,
we have
okay.
counterexamples of that.
Right, because I'm
This
just
is
going.
the second best thing we can hope for.
Okay, because I'm going back to the black hole story, right? I mean, Oppenheimer, Snyder said, look, I can make a black hole with a singularity and all that. But then people said, look, you did something very, very special. I want to show that it'll happen even generic case. And that's where Penrose came and he showed, there it was good.
Yeah.
You showed the special case it works, and then you proved that it works for the generic case. Here you're saying it's not true for the special case, but it'll be the conjecture.
Yeah.
So you just throw out those points in your multi-parameter space of problems, and you say, I'll prove it for everyone else. Am I the only one who's bothered by this?
Well, I mean, there's no, the point is that, okay, you don't, okay, so for the weak cosmic censorship conjecture, I don't have why it should be true. I don't know. I mean, there's not I think for the strong cosmic censorship conjecture, as I see in a second, as I will show in a second, there's a certain instability associated to the typical counterexamples, especially in curve, if you didn't have the word generic. So there is something which is observed by Penrose, there is a mechanism why this behavior we see in a second is actually should be maybe non-generic. For the weak cosmic censorship conjecture, it's more than some wishful thinking, actually, somehow. I mean, but yeah, I think it's sort of philosophically.
It's a philosophical
Can I just
question.
speak up in favor of the weak cosmic censorship conjecture for a moment? So first of all, I mean, if you just imagine that this very unstable solution, if you just slightly perturb it and you don't get that anymore, then there's a sense in which that's extremely fine-tuned. It's not what we see in nature, right? If you have something that's extremely fine-tuned.
Well, the point is he wants to understand why are those naked singularities unstable. I mean, I think there's not, okay, in this case, we have this bullshit instability there. So you have like a mechanism, but I think it's more.
No, actually, I'm getting there.
Philosophy of it, yeah.
Well, no,
What's what you're
it's
saying?
there's a reason from quantum gravity why you want weak cosmic censorship to be true, which is that if black holes are thermal objects, they should be typical, and that means that naked singularities cannot be typical. So that would be a quantum gravity reason why we think weak cosmic censorship should be true. Some version of it at least.
Remember, if you want to say there's all these counterexamples that are at points and there is not true. So then let's just assume that it's never true. Is that what you want? I think Christoph is saying that okay, so we can't have it always be true, so let's just hope that then most of the time it's true.
Okay,
Generically.
sorry, yeah.
Well, but yeah,
So I think it's a more optimistic philosophy than
Good.
to say,
I want to
let's
prove-
get rid of all of it.
I want to prove something,
Yeah.
yeah. Yeah, even if you got counterexamples, at least for the rest, I'll prove it,
I
yeah.
think that's
Okay.
the philosophy.
But it would be nice if there was like a principled thing that you could say, like,
Yeah.
if it satisfies these energy, then we can prove it.
Okay, done.
Christoph, before you move on, so can you also say something about the status of weak cosmic censorship with perfect fluids, either in self-similar collapse or
well, I mean, I mentioned those.
later?
No, I mentioned those results. What I just said, but
Yeah.
But okay,
So that was for the epsilon pressure.
yeah.
So for generic pressure, there's no clear picture.
Well, I think this is a very difficult problem because you also
Yeah.
have shocks.
Right,
usually,
right,
In
yeah.
a fluid situation, so. That, maybe I should look at
Okay.
the literature again, but I think there's not so much known, at least in the rigorous literature.
Okay. And in the P equal to epsilon rho case, had there been quasi-spherical collapse problems also studied? Because I know in dust people have done this.
I think, I'm not sure. I have
Okay.
to see, I think this is very recently solved.
Right.
And,
Okay, thanks.
and the next. Okay. So sort of the issue of strong cosmic censorship becomes more interesting if you allow for matter modes which allow for angular momentum and charge, since it's the Einstein vacuum equations, in which we have also the Kirch solutions. And now I'm neglecting the issue of one-ended initial data, but we don't care it for a moment because the Schwarzschild solution is also important in the case of one-ended gravitational collapse. So you can localize those conjectures also to the region of this type. Okay, so in the weak cosmic and the strong cosmic censorship conjecture, sort of the result which I mentioned before which is also, I think, quite remarkable. 2017 is actually we can give a definitive result. Let's say all vacuum space times settling down. Now the curve for which is sub-extremal curve at settling down to sub-extremal polynomially. I write it like this now. It's not quite true. So okay, maybe it's, but I have to explain a little. So if you look at the two-ended case of this type, and you have the exact Kerr data, what you have is actually that you have this Cauchy horizon here and there, across which the solution is smoothly extendable, and any such extension is non-unique. Okay. There is a favorite extension if you impose, I mean, if you impose real analyticity, then you can attach this time-like singularity there, or whatever. But we don't care about this because this is a very special extension. There's no reason why we would prefer this extension. In fact, it's not. And maximum global hyperbolic development of data posed on this sort of complete initial data set actually gives rise to this picture. I should also say that real analyticity is sort of a strange assumption for hyperbolic PDEs because it violates the causality. So this is why we don't extend it in a particular way. So it turns out that actually small perturbations of this initial data will lead to small perturbations of the solutions, or it will lead to perturbations of the solution. And if you assume now that the exterior occur stable in the sub-extreme case, and you have the expected decay rate of the exterior towards sort of a slight different curve is slightly in parameters, then what they prove actually is that the interior structure remains the same in the sense that the Penrose diagram looks also like this, and you have a Cauchy horizon. It was previously believed that actually that Cauchy horizon is unstable, and you should generically sort of perturbations that you maybe even get the space accent. But this is not the case. So what they actually prove is that you still have a null boundary, and moreover, that null boundary is C0 extendable. Okay? So now, assuming the stability of the exterior region, which I think we can all agree on, and the conjecture decay rate, which is certain polynomial, then they prove that the C0 formulation is false. Okay.
So in this case, the Cauchy surface does not become singular.
The Cauchy
So the Cauchy horizon does not become singular.
So it becomes, so that's a good question, and I will address this in a second.
Yeah, I was just wondering whether this polynomial gets rid of the blue shift instability somehow.
It is not. That's exactly the point.
Okay.
So the blue shift instability is still triggered by the polynomial.
Okay.
And this is exactly the reason what Penrose suggested that the Cauchy horizon is unstable, but it is not strong enough to trigger an instability or like an inextendability as strong as is in the Schwarzschild case of Oppenheimer's types. So you have still C0 extension. So you can extend across here as C0 naturally.
Oh, wow. Okay.
So it is actually quite remarkable. Because so it puts this formulation to rest. And what is the correct? Okay. So this has been already observed by toy models in spherical symmetry and so on, but I think proving it for the Einstein vacuum equations, maybe I should have said this is for the Einstein vacuum. No, I said is actually quite remarkable. So the correct formulation, or like the revised formulation of strong cosmic censorship, and this is the one that we like true, and this is the state of the art as a C0 Lorentzian manifold with L2 Christoph symmetries. So now you also want that you require that the Christoph symbols. I mean, you're happy if the Christoph symbols at least are non-square integer. You should think that this corresponds to like H1, if you like to somewhere. So the hope is that while those spacetimes are or open set C0 extendable, the hope is that at least that their Christoph symbols are not square integrable. And this is sort of well motivated because this is what this is what sort of you require for formulating the Einstein equations in a weak sense.
So what does square integrable mean here? I
It
mean, I
means-
got a boundary
So it means
and
just
I'm
that-
extending the metric in a C0 fashion, right?
Okay, yeah. So you're happy if the square integral of, let's say, a space-time region of if this is infinite. So you're happy if like, okay, if for any extension in the generic class, if you integrate the Christoph symbols in a set like this,
Yeah.
then this integral is infinite.
Will become infinite. You
Yeah.
cannot make it finite.
Yeah.
That's what the statement
Yeah.
is. Okay.
But okay, this is an open problem. There
But it's
is
equivalent to saying that you cannot patch up another universe across this surface
another universe.
or whatever, another
Another
space
direct manifold
manifold
for
across.
which you can extend it in a way that it's both continuous and moreover that the first derivatives are known too. Yeah.
So physically, does it mean that on that surface there is some matter, some
And it's
stress
developed
tensor,
essentially.
which is singular?
I mean, okay, this is for the Einstein vacuum. So there's no
Right,
matter. So,
right.
But
Okay.
I mean, in some sense, it means that we have energy flow,
Energy blow. I see.
mean-
Okay.
like the
But-
H.
And that comes from gravitational waves.
I mean, okay, you can
There's
entertain this.
nothing
Okay,
else.
let's say.
There's nothing else. It's vacuum.
Okay.
So the reason why we like as mathematicians to entertain vacuum is because it's not because we think this is how black holes are formed and so on. I mean, it's clear, but is that it's sort of the cleanest statement you can do, and everything you say about vacuum is necessarily true
Yeah,
for gravitation,
Exactly.
and it's not an artifact of the matter model you're using. And if you prove it for vacuum, then it's inevitable because okay, no matter what theory of classical gravity you use, you always have to swing because vacuum is contained in all.
Is there some sense in this formulation where you're assuming you can make a black hole out of gravitational waves?
Yes, actually, this is a theorem by Christoph Kehle, which proves that you can form
You
gravitational
can,
waves from. It is. Yeah. So
And is this roughly what is meant by this integral being infinite?
It's like the energy sum. It's like the first derivative of the metric. That's what Christoph symbols are, and they are not so oriented. So yeah, I mean, if you look at the wave equation, then the analysis. So if you look at scalar waves, for instance, so I should maybe say that all those results you can entertain them at least around curve, for instance, by looking at the linear analog, for which you look at just the scalar wave, the fixed spectrum, so you don't take back reaction into account, and you want to understand whether the solution to the linear wave equation or to scalar waves blow up at the Cauchy horizon for generic data. And so this formulation would correspond that this comes generically infinite. And if you just had the C0 formulation, you would know whether this remains the continuous function across the Cauchy horizon for generic solution. Okay, I'm going far too slow. Maybe I want to say something. Okay, I should say that there's a lot of work. This actually is strong consistency. There's a lot of traditional work for dust and also lots of work on especially symmetric models and various things have been proved also in the positive direction. Which okay, there's no way I can overview all of this. I should maybe say that I think one is not so far away from being able to prove maybe at least the validity of strong cosmic censorship around curve. To prove the validity of strong cosmic censorship for any of those conjectures, you'd have to address the full space of solutions, which good luck. But you you can first address it around an explicit solution in the neighborhood. And I think that should be, I think that that's sort of tractable in the future to possibly prove around the curve solution. Okay, let me say something because I want to also mention this in one of my own works, which sort of doesn't fit exactly in what I just said, but I hope you don't mind. So you can also entertain this issue in the case of a positive cosmological constant and a negative. So what you have in the positive cosmological constant that you expect exponential decay of the exterior. So this means that if you just look at the if you just look at this part of the diagram, it means that you converge generically to current de Sitter at an exponential rate. Okay. And this exponential rate is now in competition with the blue shift instability of the Cauchy rise. So in this case, even in the positive cosmological constant case, even the H1 formula, so that formulation I gave you may be in danger. And this is also something interesting to understand. And there have been also numerous works on various time models. So now I want to say my own work, in which case I studied the case of anti-de Sitter, as I'm talking the anti-de Sitter black hole, in which case you only have one of the log decay. So you should say this is not just for the wave. So for the Einstein equation, this is a very, maybe you have an instability and so on. But for the wave equation, so box phi were maybe you want to say the from the wave equation. You have only one of the log decay on the exterior for the wave equation. So this very slow decay actually sort of may even mean that blue shift instability somehow is stronger than it used to be in the other case. Because now, remember in the F flat case, you have polynomial. And what I proved is that, in my PhD, what I proved is that it turns out that P generically, pointwise, blows up at the Cauchy horizon. This is the solution to the wave equation. I got those data there. I put the Schley conditions there, reflecting boundary conditions there. That phi blows up at the Cauchy horizon, pointwise, if the black hole parameters A and M satisfy certain number theoretic properties. Satisfy number theoretic properties. These are certain Diophantine properties and properties. And these properties tell whether, or like ask whether A and M, or a suitable ratio of them, can be approximated by a rational number sufficiently fast. And if that is the case, then you have blow up of the scalar field. And these properties are actually, you can show, now we're going a little bit mathematical work. They're bare generic and Lebesgue exceptional. So these are very weird sets. So they're generic in the topological sense, but they're generic, they're exceptional in the measured theoretical sense. And so these are natural numbers with these classifications genericity, they pop up also in what's known as Diophantine approximations. And it turns out that you can prove blow up if this is the case. So I also claim, and I have not proved this, that if these are not satisfied, then you have problems. So the proof strongly suggests this, but okay. Do some work.
So this does not depend on lambda?
So I said, that's a great point. I said lambda in order for this discussion to be nice. So you have to be on this.
Okay. Because I was thinking.
You're absolutely right. There's
Right.
a scaling. Sorry for.
So these things are some resonances?
Yeah. These are resonances. So actually, the funny thing is that they don't have anything to do with the, like, not necessarily with the blue shift instability.
Mhm.
The blue shift instability is something which gives you exactly law of equilibrium. but low above on the level of C0, it doesn't really see the difference. It has to do with the quadrant mode spectrum. I prefer the quasi-mode spectrum of the exterior. And there's certain scattering resonances in the interior, which have to do with the frequency equal to 0 of the push horizon. And frequency equal to 0 of the push horizon, you think of the killing generator because of its rotation, actually is omega in the decomposite pictures, omega minus times n. And what happens is that, and then you have also the quasi-normal modes, they're sort of large frequency. And what can happen is that the quasi-normal modes are actually resonant sufficiently with those frequencies of this Cauchy horizons, then you can trigger this instability. That's exactly the mathematics.
And these conditions are in line with the inequality A smaller or we call them N.
So this is for the sub-extreme range. There is actually
right. So yeah. So there.
So there is also a range in which the exterior even doesn't have 1 over log decay. So there is a range of parameters which are in the sub-extremal range for Kerr ADS, which have the property that you have growing modes on the exterior. So I know those. So these are, I only look at the parameters in the sub-extremal range, which are 1 over log decay. I mean, these are sort of the biggest set you can reasonably entertain this. Okay, now, well, I think maybe that's all I wanted to say, but give me 1 second. Maybe I want to mention one more thing, and particularly something which is related to something which I've done recently more. This is about the extremal case. So the extremal case is, of course, non-generic, because it's hit by Q equals M. But what I think is interesting is actually exactly because in the extremal case, Penner's diagram looks a bit different. Yes, it looks something like this. So we forget always about this part. Right? I mean, this is the physical unrealistic, not so important. So the point, however, is that you don't have the redshift here. So the redshift factor is equal to 0 in the extreme case. Temperature is equal to 0. Surface gravity is equal to 0. So you expect slower decay if you decay. Let's say for the full vacuum, or even for linear wave equations. So for extreme resonance, you have decay of towards I plus. You have stability of the exterior region. And what is true that you don't have the redshift. However, at the same time, you also don't have the blue shift. Okay. So the extremal case is sort of interesting because on the one hand, the exterior decay is slower, but on the other hand, you don't have this blue shift stability. Because the blue shift factor is also equal to 0. So it is actually, I think one does not know whether even for the linear wave equation on Reisner stream occur, whether for generic data or for any data which arise from sort of say from the data posted hypersurface like this, you blow up at the push even for the linear wave. I think that's sort of something I think it's quite interesting. Yeah. But yeah, of course it is not relevant because it will be generic. But that's not.
But if, as you say, it comes at the threshold of black hole formation.
So maybe I can give one last comment. I'm sorry. If you feel free to go. So in the modular space, which I always like to draw. So here, let's say we have the complete solutions to DCG complete, or depending on what we look at on dispersive solutions. So there's Minkowski space here, and there we have the black hole solutions. So now, critical collapse is you study a one-parameter family of initial data interpolating between Minkowski and the black hole. What is interesting, and I should wanted to mention this also, is that numerically, actually, it has been found by Chortui that there exists a window on the black hole formation threshold where you have naked singularities, which have discrete subsimilar let's say naked singularities. So this was done by Chotui.
These are all spherically symmetric.
These are also symmetric. These are for the Einstein scalar field symmetry. Yeah. Thanks for clarifying this. Yeah. So actually, on that part of the boundary, you have counterexamples to weak cosmic censorship if you drop generic, but maybe now it's getting a bit too speculative. So we have proved this other result recently, where we have together with Ryan Hunger, where we have on that point we have an extremal black hole. Of course, in this we use a different matter model which allows for charge. In this case, it's extremal resonance black hole. And now, if you think that maybe actually exactly with this part, now you find. Now I'm getting too speculative, but maybe you find there counterexamples to strong conjecture it's an extremal black hole. If you go. But yeah, okay, maybe that's the first. Okay, thank you for your attention.